Fine, let's start. We built the best detector on Earth, buried it a mile underground, filled it with 10 tons of liquid xenon cold enough to freeze your breath solid, ran it for over 400 days, 250 scientists, decades of preparation, and it found nothing. Number 10. The ghost in the detector. Here's the problem we've been sitting with for 90 years. Roughly 85% of all the matter in the universe isn't made of anything we've ever touched, seen, or detected. It doesn't emit light, doesn't absorb it, doesn't interact with your hand, or the Earth, or the detector we buried in South Dakota. We only know it exists because of what it does to gravity, how galaxies spin faster than they should, how light bends in ways that don't make sense without something invisible holding everything together. We call it dark matter, which is a polite way of saying we have no idea what it is. Our best candidate for decades has been a class of particles called WIMPs, weakly interacting massive particles, theoretically elegant, predicted by multiple extensions of the standard model, the kind of thing that on paper should show up in a sensitive enough detector. So we built one. The Luke Zeppelin experiment at the Sanford Underground Research Facility in South Dakota, a mile of rock above it to shield it from cosmic rays, 10 tons of liquid xenon so pure it makes pharmaceutical grade look sloppy. The idea being, if a WIMP drifts through the Earth and happens to clip a xenon nucleus, it leaves a tiny flash of light, just enough for sensors to catch it. They collected 417 days of data. March 2023 through April 2025. The largest dataset ever collected by a dark matter detector. Nothing. But here's the thing. The detector worked perfectly. In fact, it worked so well it started picking up solar neutrinos, particles so ghostly they pass through entire planets like they're not there, as background interference. The machine has now crossed into what physicists call the neutrino fog, a zone where the signal from neutrinos and the hypothetical signal from dark matter are virtually indistinguishable. We may have built the best tool we're capable of building, and nature may have arranged things such that the answer sits just behind a wall we can't see through. 85% of all matter, and we can't find a single piece of it. It isn't hiding. It's everywhere. We're swimming in it right now. We just can't feel it. Number 9. The corpse that screams. Somewhere in the universe, roughly every minute, something fires off a burst of radio energy so intense it releases more power in a few milliseconds than our sun produces in an entire day. The burst lasts about as long as a blink. Then it's gone. These are fast radio bursts, first discovered in 2007, buried in archival data from the Parkes Radio Telescope in Australia. A graduate student named David Narkovich found it while working with his supervisor, Duncan Lorimer. The signal was so bright, so brief, and so unlike anything cataloged, they almost didn't believe it. By 2025, we've detected thousands of them. Some repeat, most don't. They come from galaxies billions of light years away. And the leading theory, supported by a detection inside our own galaxy in 2020, is that they're produced by magnetaires, neutron stars with magnetic fields so extreme that starquakes in their crusts crack like a whip across space-time. Good theory, solid evidence, case mostly closed. Except the universe keeps reading the wrong script. In February 2024, a repeating burst fired 21 times. When astronomers traced it back to its source, they found an 11.3 billion-year-old galaxy, one so ancient it stopped forming stars billions of years ago. A dead galaxy. Cold. Quiet. And the burst came from the very edge of it, 130,000 light-years from the galactic center, a place where, by every model we have, the kind of object thought to produce these bursts simply cannot form. Then in March 2025, the brightest fast radio burst ever recorded went off. CHIME, a radio telescope array in British Columbia, caught it. They traced it to a galaxy called NGC 4141, about 130 million light-years away. They pointed the James Webb Space Telescope at the exact location. What they found was a faint infrared smudge, possibly a red giant star near the end of its life, being slowly drained by a neutron star companion. That source had been sitting in Kim's field of view every single day for 7 years before it went off. 7 years of silence. Then one of the brightest events in the observable universe. Then silence again. There's something about the universe that finds our categories and quietly ignores them. Space is not empty, it's just quiet. And sometimes something in that quiet decides to say hello. Number 8, the impossible babies. When the James Webb Space Telescope opened its eyes in 2022, we knew it would see further than anything before it. We had predictions, models, simulations refined over decades of work. We knew roughly what the early universe should look like. We were wrong. Within months, JWST was returning images of massive, fully formed galaxies existing just 500 to 700 million years after the Big Bang. To put that in perspective, the universe is 13.8 billion years old. These galaxies were already enormous before it was even 4% of its current age. Several of them appeared more massive than the Milky Way, a galaxy that had over 13 billion years to grow into what it is. The phrase that started circulating among cosmologists was impossible galaxies, which is not a phrase cosmologists use lightly. Now, the story gets more nuanced from there. In 2025, NASA published a study that resolved most of the alarm. It turned out many of these objects weren't actually as massive as they looked. They contained active black holes, pouring out enormous amounts of light, making their host galaxies appear much bigger and brighter than they actually were. Strip out those black hole-powered imposters, and most of the crisis goes away. But not all of it. After removing those objects, there are still roughly twice as many large early galaxies as standard cosmology predicts. Something in the early universe was forming stars faster than our models allow. We don't know what. And then there's the big wheel. In early 2025, JWST found a galaxy, large, ancient, clearly from the first 2 billion years of the universe, with a beautiful spiral structure. Arms sweeping outward the way the Milky Ways do. That shouldn't be there. In the early universe, galaxies are expected to be chaotic, irregular, still colliding and merging. Spiral structure takes time to settle into. Billions of years of time. This one didn't wait. Maybe the universe was just better at growing up than we thought. Or maybe there's something about how early structures formed that we've been getting fundamentally wrong. The universe organized itself with a patience it shouldn't have had. Number 7. The name that shouldn't exist. This one starts with a map. The most detailed map ever made of the oldest light in the universe. The cosmic microwave background, a faint glow of radiation left over from about 380,000 years after the Big Bang. It covers the entire sky. Temperature variations in it, tiny fractions of a degree, encode the seeds of everything that would eventually become galaxies, stars, planets, us. The map was made by the WMAP satellite in the early 2000s, and later refined to extraordinary precision by the European Space Agency's Planck satellite. Both were engineering triumphs. Both returned data that, on almost every scale, matched our models beautifully. Almost. At the very largest scales, patterns so big they span the entire observable sky, something was off. The temperature variations weren't randomly oriented the way they should be. The two largest patterns, called the quadrupole and the octopole, had their axes pointing in almost the same direction. That alone was strange. But then astronomers noticed where that direction pointed. Toward the plane of our solar system. The largest structures in the oldest light in the universe, structures that formed when the cosmos was less than 400,000 years old, structures separated from us by 13 billion light years, appear to be aligned with the plane in which Earth orbits the Sun. Physicists named it the axis of evil. Half wry, half genuinely alarmed. When Planck's results came in 2013, most researchers were hoping the anomaly would dissolve. Better data, better instruments, surely it would go away. It didn't. Dominic Schwartz of the University of Bielefeld said at the time, "For a long time, part of the community was hoping that this would go away, but it hasn't." The physicist Lawrence Krauss, characteristically blunt, laid out the options. The result is either telling us all of science is wrong and we're somehow at the center of the universe, or the data is contaminated, or there's something deeply strange about the microwave background that we don't understand. The mainstream view is contamination. That some local signal, dust in our own galaxy, some instrumental artifact, is bleeding into the measurement at the largest scales. And a 2016 study found no evidence for anisotropy when they controlled for this. So maybe it's nothing. But the Planck data strengthened it, not weakened it, and we're still here looking at the oldest light in the universe and finding our own address written in it. Number 6, the proton that won't die. Every atom in your body is built around a nucleus. That nucleus is made of protons and neutrons. The proton, as far as we know, just sits there. Stable. Eternal. It doesn't decay, it doesn't change. Except according to our best unified theories of physics, it should. Grand Unified Theories, GUTs, are frameworks that try to bring 3 of the 4 fundamental forces together under a single umbrella. They're not crackpot ideas, they're mathematically rigorous, they explain things the standard model doesn't, and they receive serious attention from serious physicists. And virtually all of them predict that the proton is not actually stable. It should eventually decay into lighter particles. The predicted lifetime is staggeringly long. The original estimate from the 1974 Georgi Glashow model was around 10 to the 29th years, a number so large that it makes the age of the universe look like an afternoon. But crucially, if you have enough protons, you can watch for the rare event statistically. So in the 1980s, physicists built the detectors to do exactly that. The most famous is Super Kamiokande in Japan, 50,000 tons of ultra-pure water sitting inside a mountain, lined with thousands of light sensors, watched by physicists with extraordinary patience. They've been watching since 1996. No proton has decayed. The original GUT prediction ruled out. The current lower bound on the proton's lifetime is greater than 10 to the 34 years. The models have just adjusted upward, over, and over, staying ahead of the experimental limits. But here's the detail that earns its place in this video. Super Kamiokande was built for proton decay. It has found 0 proton decays, but in 1987, while it was watching, a star in the Large Magellanic Cloud exploded. Supernova, 1987 AIM. And the neutrinos from that explosion, traveling 160,000 light years, arrived at Super K and were detected. The detector built to answer one question answered a completely different one instead. That detection contributed to a Nobel Prize. Hyper Kamiokande is now under construction. 8 times the fiducial volume of its predecessor. It should begin taking data in 2028. It will either find proton decay or push the lifetime limits so high that many of our favorite unified theories are simply ruled out. The particle we're made of might live forever, or it might not. And the difference matters enormously for whether we understand the universe we're still watching. Number 5. The void we live in. In 2013, 3 astronomers, Ryan Keenan, Amy Barger, and Lennox Cowie, published a paper with an unsettling conclusion. When they mapped the distribution of galaxies in our cosmic neighborhood, they found fewer of them than expected. A lot fewer. In a sphere roughly 2 billion light-years across, centered uncomfortably close to our own galaxy, matter appeared to be 20 to 50% less dense than the cosmic average. We might live inside the largest underdense region ever mapped. A cosmic void. A bubble of relative emptiness in the fabric of large-scale structure. This would be a strange and interesting fact on its own, but it connects to something bigger. You've probably heard of the Hubble tension. If you haven't, it's been called the most significant unsolved problem in cosmology. When astronomers measure the expansion rate of the universe using early universe data, the CMB, the fingerprint of sound waves frozen into the distribution of galaxies, they get a value of about 67.4 kilometers per second per megaparsec. When they measure it locally, using Cepheid stars and supernovae as distance markers, they consistently get about 73. That's a 5 sigma discrepancy. In physics, 5 sigma is the threshold at which you declare a discovery. This isn't a rounding error. Both measurements have been checked by multiple independent teams, and in 2024, the James Webb Space Telescope confirmed the local value is accurate. Something is genuinely wrong with our picture. The KBC void might be the explanation. If we're sitting near the center of an enormous underdense region, galaxies in our neighborhood are being pulled outward toward the denser surroundings. They're flowing away from us slightly faster than they would be in an average patch of universe. That would make our local measurement of expansion appear inflated. Not because the universe is expanding faster here, but because we're in a gravitational valley and everything around us is streaming uphill. At the Royal Astronomical Society's National Astronomy meeting in 2025, A new analysis of baryon acoustic oscillation data showed that a void model is approximately 100 million times more statistically likely than the standard void-free model consistent with the Planck cosmology. 100 million times more likely. Except, a void this large and this deep is itself a 6 sigma deviation from what the standard model of cosmology predicts. The universe is supposed to be smooth and uniform on large scales. A bubble this big shouldn't exist, so if the void is real and resolves the Hubble tension, it simultaneously breaks the model that the Hubble tension was threatening. We may have been misreading the expansion of the universe because of where we're standing in it. We're like scientists trying to measure sea level from the bottom of a valley, not realizing the ground beneath them is lower than average. The universe looks different from here. And here may be the problem. Number 4. The book that burns. In 1974, Stephen Hawking published a calculation showing that black holes aren't truly black. They glow, faintly, slowly, through a quantum process at their event horizon. Pairs of virtual particles pop into existence constantly in the vacuum near the horizon. One falls in, one escapes. The escaping one carries energy away. Over an incomprehensibly long period of time, this process causes the black hole to slowly evaporate and disappear. This was a remarkable result. It fused quantum mechanics with general relativity in a way nothing had before. It also created a problem that nobody has solved in 50 years. Here's the issue. Quantum mechanics is built on a principle called unitarity. Information cannot be destroyed. The state of a physical system at any point in time contains, in principle, complete information about its past and future. It can be scrambled, compressed, hidden, but not annihilated. The universe is, in this sense, perfectly reversible. Every event is encoded in what follows it. Hawking radiation doesn't work that way. The radiation that comes out of an evaporating black hole is thermal. It's random noise. It carries no information about what fell in. A black hole could form from a collapsing star, or from a trillion encyclopedias, or from antimatter. And the radiation that comes out looks the same. When the black hole is gone, all that information, everything about everything that ever crossed the horizon, appears to be simply erased. If that's true, quantum mechanics is broken. The universe has a delete key. Hawking himself wrestled with this for decades. In 2015, at a conference in Stockholm, he proposed that information isn't lost. It's stored in soft hair, subtle quantum imprints on the event horizon, carried out in the radiation at the very end of the black hole's life. Most physicists thought the idea was incomplete. An interesting direction, not a solution. He died in 2018. In November 2025, physicists gathered at Stony Brook University for the Paradox's 50th anniversary conference. The organizers described diverse views on the resolution. That's academic for, we still don't agree. The frustrating part isn't that we don't know the answer. It's that whatever the answer turns out to be, something we currently believe about nature has to be wrong. Either information is destroyed and quantum mechanics needs to be rewritten, or it escapes, and general relativity's description of event horizons is somehow incomplete. Pick your poison. Hawking opened a door in 1974. 50 years later, we're still standing in the doorway, not because we haven't tried, because the universe hasn't decided to tell us which room we're walking into. Number 3, 1 in a billion. Stop for a moment and think about what it would mean for the universe to be completely symmetric, for matter and antimatter to be created in perfectly equal quantities in the first moments after the Big Bang. It means nothing you're looking at would exist. No stars, no galaxies, no planets, no atoms. Matter and antimatter would have annihilated each other completely. Proton by proton, electron by positron, leaving a universe of pure radiation. Photons in all directions, carrying the memory of matter that almost was, that's what the math predicts. Perfect symmetry, total annihilation. An empty universe. Instead, something tipped the balance. Somehow, for every billion matter-antimatter pairs that annihilated each other, one extra particle of matter was left over. Just one. The entire observable universe, every star you can see, every atom in your body, every planet and galaxy and nebula across 14 billion light years, is that left over. The rounding error at the end of a catastrophic equation, we don't know what caused it. The asymmetry we do understand, tiny differences in how particles and antiparticles decay, first observed in the Kaon system in 1964, later confirmed in B machines at accelerators in the 2000s, is about 10 billion times too small to explain the imbalance we observe. The math accounts for a trickle. The universe required a flood. And here's what makes it stranger. The most obvious escape route, that maybe antimatter falls differently, that gravity treats matter and antimatter asymmetrically, producing the imbalance that way, has essentially been closed. Experiments with antihydrogen, the antimatter equivalent of a hydrogen atom, have confirmed that antimatter responds to gravity the same way matter does. Within current measurement precision, it falls down. So gravity isn't it, the known CP violation isn't enough. Something else happened in the first fractions of a second after the Big Bang, some process that tilted the scales just slightly, and then vanished, leaving us a universe and no record of how it did it. Hyper Kamiokande, the next generation Japanese neutrino detector now under construction, is specifically designed to search for this asymmetry in the behavior of neutrinos. Neutrinos are the most ghost-like particles we know, barely interacting with anything, and they may be the messenger carrying the answer. If their matter-antimatter asymmetry is large enough, it could drive a process called leptogenesis that cascades into the baryon asymmetry we observe. If it's not there, we're out of mainstream candidates. We'd be looking at genuinely new physics. Every atom you've ever encountered is a survivor. It exists because something we can't yet explain decided, very briefly, to favor matter over nothing. That's not a metaphor. It's just what happened. Number 2. The number that shouldn't be. Imagine our best physical theory, the one we test with particle accelerators and confirm with extraordinary precision, makes a prediction about the universe, and the prediction is off. Not by a factor of 2, not by an order of magnitude, by a factor of 10 to the power of 120. Write that out. 1 followed by 120 zeros. If you started listing those zeros at the beginning of the universe, you'd still be listing them now. This is the cosmological constant problem, and it may be the most embarrassing thing in all of science. Here's what's happening. Quantum field theory, the framework underlying all of particle physics, experimentally verified to extraordinary precision, predicts that empty space is not actually empty. It's filled with quantum fluctuations, virtual particle pairs constantly winking in and out of existence. All of this activity carries energy, zero-point energy, vacuum energy. And according to the equations, it should be enormous. That energy acts like a cosmological constant, a pressure built into the fabric of space-time that drives the universe's expansion. So when physicists calculate the vacuum energy from quantum field theory and compare it to what we actually observe for the cosmological constant, they should get a match. They don't. The theoretical value is 10 to the power of 120 times larger than what we measure. Wolfgang Pauli noticed this problem in the 1920s. He calculated that if the vacuum energy were as large as quantum theory suggests, the radius of the universe would not even reach to the moon. He found this amusing. Nobody else paid much attention. In 1967, Yakov Zeldovich formalized the calculation and the alarm began. In 1998, dark energy was discovered. The accelerating expansion of the universe confirmed that some form of vacuum energy is real and non-zero. The cosmological constant wasn't zero after all, it was just unimaginably small. And that made the discrepancy not just a theoretical puzzle, but a genuine confrontation between what nature does and what our best theory says it must do. And then, in 2012, physicists at CERN discovered the Higgs boson, a triumph, the last missing piece of the Standard Model. Except it also added another enormous contribution to the theoretical vacuum energy, one that also somehow nearly perfectly cancels out to leave the tiny observed value. The discovery that completed particle physics also deepened its most embarrassing problem. There's no known mechanism that makes this cancellation happen. It would require 2 enormous, independently calculated quantities to agree to 120 decimal places, for no reason. By coincidence, physicists call this fine-tuning. It's a polite term. What they mean is, we have no idea. The universe exists in a form that our best theory of matter says it shouldn't. It's gentle and gradual and structured and habitable. By the quantum field theory prediction, it should be an unrecognizable froth of infinite energy. It isn't, and we don't know why it isn't. We are standing inside a universe that our equations say can't exist. That's not hyperbole, that's just the math. Number 1. The question before the first question. General relativity, Einstein's theory of gravity, the most geometrically beautiful equation in physics, makes a prediction about the Big Bang. Run the expansion of the universe backward, compress everything into smaller and smaller volumes, increase the density without limit, and you arrive at a singularity, a point of infinite density, infinite temperature, infinite curvature, a place where the equations stop working. More than that, time itself in general relativity emerges from the structure of space-time. And if space-time began at the singularity, then time began there too. Which means asking what happened before the Big Bang is like asking what's north of the North Pole. The question isn't hard to answer. It's structurally malformed. There is no before. That's the official position. And it may be correct, but multiple serious framework, not fringe ideas, but mathematically coherent theories developed by physicists at major institutions, propose that something did exist before the bang. In the Big Bounce model, our universe is the rebound of a previous collapsing universe. In the pre-Big Bang scenario developed from string theory in the 1990s, there was an accelerating expansion before the bang that mirrors the expansion after it. In cyclic cosmology developed by Paul Steinhardt and Neil Turok, universes collide, collapse, and are reborn in an endless loop. None of these has been confirmed. None has been ruled out. And here's the part that should sit with you. There is a mathematical theorem that prevents us from ever observing the conditions that preceded inflation, the rapid expansion in the universe's earliest moments. The theorem works the same way as an event horizon around a black hole. Information from before that boundary cannot reach us. It's not that we lack the technology, it's that the physics itself draws a curtain, and we are on the wrong side of it. Now. In 2025, a physicist named Professor Enrique Gastañaga published a new model proposing something extraordinary. Dark matter, the invisible substance we've been hunting for 90 years, the stuff that makes up 85% of all matter, the thing the LUX Zeppelin detector couldn't find, might be relic black holes. Black holes that formed in a contracting universe before our Big Bang, survived the bounce, and now populate our universe as fossils from before. Think about what that means. The two deepest unsolved questions in cosmology, what came before the Big Bang and what is dark matter, may be the same question. The thing we can't find and the place we can't see might be one and the same mystery, waiting on the other side of a wall we may never be able to breach. We've been asking, what is dark matter for almost a century? And the answer might be everything that survived from the universe that came before ours. We don't know if there was a before. We don't know if we can ever know. The beginning of our universe may be permanently sealed, not by our limitations as scientists, but by the architecture of reality itself. Sean Carroll, one of the physicists working seriously on these questions, put it simply. He said, "I think it's completely preposterous that in the year 2025, we should understand the beginning of the universe. Why not in the year 2,000,025? He wasn't being dismissive, he was being honest. We are extraordinarily young at this. The questions are old. The universe has had 13.8 billion years to arrange itself into something we spend a few decades trying to decipher. It keeps its secrets well. Maybe that's what science actually is, not the accumulation of answers, but the slow, humbling process of learning what the questions actually mean." Thank you for watching and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next one.